the described situation, backfeeding was likely occurring on the grounded conductor, also known as the neutral, because the transfer switch does not switch the neutral. When the grounded conductor is not switched, it can create a pathway for current to flow back into the utility grid, which is a safety hazard for utility workers. To prevent backfeeding, the grounded conductor must be switched in conjunction with the ungrounded conductors, also known as hot wires. The transfer switch receptacle provides 4 blades to accommodate both 3-prong and 4-prong generator inlets. Generators with 3-prong inlets do not have a dedicated ground pin, instead using the neutral conductor as a combined neutral and ground. The 4th blade on the transfer switch receptacle is intended to connect to the generator frame or ground screw, providing a dedicated ground path. When using a 3-prong generator inlet, the 4th blade should be taped to a cover to prevent unintentional contact with the ground terminal on the transfer switch. While it is possible to detect backfeeding by measuring current on the grounded conductor, this method is not always reliable. A better way to check for backfeeding is to use a clamp-on ammeter to measure current on all 3 ungrounded conductors, which are the hot wires. If any significant current is present on any of the hot wires while the generator is running and the utility power is off, backfeeding is occurring. If the transfer switch does not switch the grounded conductor, it should be replaced to prevent backfeeding. It is recommended to hire a qualified electrician if one is not comfortable performing this upgrade. Here's a more detailed explanation of backfeeding and how to prevent it. A transfer switch is a device that allows to safely connect a generator to the home's electrical system during a power outage. It isolates the home's wiring from the utility grid, preventing backfeeding. Backfeeding is a dangerous situation where electricity from the generator flows back into the utility grid. This can happen if the transfer switch does not properly isolate the home's wiring. Backfeeding poses a serious risk to utility workers who may be working on the power lines, assuming they are de-energized. It could also damage the generator and the home's electrical system. There are 2 main types of transfer switches: manual and automatic. A manual transfer switch requires one to manually switch between the utility power and the generator power. An automatic transfer switch automatically switches to the generator power when it detects a power outage. There are several reasons why the grounded conductor, or neutral, should be switched in a transfer switch. Firstly, safety. Switching the neutral prevents backfeeding, which, as mentioned, is a safety hazard for utility workers. Secondly, preventing ground loops. When the neutral is not switched, it can create a ground loop, which can cause unwanted current to flow through the grounding system. This can lead to electrical noise and interference. Thirdly, compliance with electrical codes. Many electrical codes require the neutral to be switched in transfer switches to ensure safety. Here's a step-by-step guide on how to check for backfeeding. 1. Turn off all the breakers in the main electrical panel. 2. Start the generator and let it run for a few minutes. 3. Use a clamp-on ammeter to measure the current on each of the hot wires coming from the generator. 4. If any current is present on any of the hot wires, backfeeding is occurring. If backfeeding is detected, take the following corrective actions. 1. Immediately turn off the generator. 2. Disconnect the generator from the transfer switch. 3. Replace the transfer switch with one that switches the neutral. When selecting a transfer switch, consider the following factors. 1. The size of the generator. The transfer switch must be rated for the maximum current output of the generator. 2. The type of transfer switch. Choose between a manual or automatic transfer switch, depending on needs and preferences. 3. Neutral switching. Ensure that the transfer switch switches the neutral conductor. 4. Compliance with electrical codes. Make sure that the transfer switch meets all applicable electrical codes. Grounding is an essential aspect of electrical safety, and it plays a crucial role in preventing electrical shock and equipment damage. Understanding grounding principles is crucial for anyone working with electrical systems. Grounding refers to the intentional connection of electrical circuits and equipment to the earth. This connection provides a low impedance path for fault current to flow back to the source, which helps to quickly trip circuit breakers or fuses, disconnecting the faulty circuit and preventing electrical hazards. Grounding serves several important purposes. Firstly, it provides a path for fault current. In the event of a short circuit or insulation failure, fault current will flow through the grounding system back to the source. This high current will quickly trip the overcurrent protection device, such as a circuit breaker or fuse, energizing the circuit and preventing electrical shock or fire. Secondly, it limits voltage to ground. Grounding helps to stabilize the voltage of electrical systems with respect to ground. This is important for preventing voltage fluctuations and reducing the risk of electrical shock. Thirdly, it reduces electrical noise. Grounding can help to reduce electrical noise and interference in sensitive electronic equipment. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding refers to the connection of non-current carrying metal parts of electrical equipment to ground. This includes things like the metal enclosures of appliances, motors, and electrical panels. Equipment grounding provides a path for fault current to flow back to the source in the event of an insulation failure, protecting people from electrical shock. System grounding refers to the grounding of the neutral point of an electrical system. This is typically done at the service entrance of a building. System grounding helps to stabilize the voltage of the electrical system and provides a path for fault current to flow back to the source. Grounding electrodes are used to connect the grounding system to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The grounding electrode must be properly sized and installed to provide a low impedance connection to the earth. The size of the grounding electrode is typically determined by the size of the electrical system. Grounding conductors are used to connect electrical equipment and systems to the grounding electrode. Grounding conductors must be properly sized and installed to provide a low impedance path for fault current. The size of the grounding conductor is typically determined by the size of the circuit it is serving. Bonding refers to the connection of different metal parts of an electrical system to create a continuous electrical path. Bonding is important for ensuring that all metal parts are at the same potential, which reduces the risk of electrical shock. Bonding conductors are used to connect different metal parts of an electrical system. Bonding conductors must be properly sized and installed to provide a low impedance path for fault current. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly trip the circuit breaker if they detect a ground fault. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in many areas of the home, such as bathrooms, kitchens, and outdoor areas. Proper grounding is essential for electrical safety. Regular inspection and testing of the grounding system is important to ensure that it is functioning properly. If any problems are found, they should be corrected immediately. Always consult with a qualified electrician for any electrical work. Working with electricity can be dangerous, and it is important to take precautions to protect self and others from electrical shock. Here are some additional details regarding grounding and bonding. The National Electrical Code, also known as the NEC, provides comprehensive requirements for grounding and bonding electrical systems. Article 250 of the NEC covers grounding and bonding. This article provides detailed requirements for grounding electrodes, grounding conductors, bonding conductors, and ground fault protection. The NEC also specifies the minimum size of grounding and bonding conductors. The size of these conductors is determined by the size of the circuit they are serving. The NEC also requires that all metal parts of an electrical system be bonded together. This includes metal conduits, metal enclosures, and metal water pipes. The purpose of bonding is to create a continuous electrical path, which reduces the risk of electrical shock. Ground resistance is a measure of how well the grounding system is connected to the earth. A low ground resistance is desirable because it provides a better path for fault current to flow back to the source. Ground resistance can be measured using a ground resistance tester. This tester injects a small current into the grounding system and measures the voltage drop. The ground resistance is then calculated using Ohm's law. Regular testing of the grounding system is important to ensure that it is functioning properly. The NEC recommends that grounding systems be tested at least every 3 years. If the ground resistance is too high, the grounding system should be repaired or replaced. Surge protection devices, also known as SPD, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. SPD work by diverting the surge current to ground, which protects the equipment from damage. SPD should be installed at the service entrance of a building and at any sensitive electronic equipment. Electrical safety is a critical aspect of any electrical installation. Proper grounding and bonding are essential for protecting people and equipment from electrical shock and fire. Always follow the requirements of the NEC and consult with a qualified electrician for any electrical work. Here are some common grounding mistakes to avoid. Firstly, improper grounding electrode. Using an inadequate grounding electrode, such as a short ground rod or a corroded water pipe. Secondly, loose connections. Failing to make tight connections on grounding and bonding conductors. Thirdly, improper conductor sizing. Using undersized grounding and bonding conductors. Fourthly, neglecting bonding. Failing to bond metal parts of the electrical system together. Fifthly, ignoring GFCI protection. Omitting GFCI protection in areas where it is required. Sixthly, improper SPD installation. Incorrectly installing surge protection devices. Avoiding these mistakes can significantly improve the safety and reliability of the electrical system. Always prioritize safety and seek professional assistance when needed. Understanding the principles of grounding and bonding is crucial for ensuring electrical safety. By following the guidelines and best practices, one can create a safe and reliable electrical system. Additionally, understanding the role of a 4-prong receptacle versus a 3-prong receptacle in generator connections is important. The 4-prong receptacle is designed to provide a separate ground connection, while the 3-prong receptacle combines the neutral and ground connections. When using a generator with a 3-prong receptacle, it is essential to ensure that the neutral is properly bonded to the generator frame. This bonding provides a path for fault current to flow back to the generator, which helps to trip the circuit breaker in the event of a fault. However, when connecting a generator with a 3-prong receptacle to a transfer switch with a 4-prong receptacle, it is important to take extra care to avoid creating a ground loop. A ground loop can occur when there are multiple paths for current to flow to ground, which can cause unwanted current to flow through the grounding system. To prevent a ground loop, it is recommended to either use the generator with a 4-prong receptacle or to modify the transfer switch to switch the neutral conductor. Switching the neutral conductor ensures that there is only one path for current to flow to ground, which eliminates the possibility of a ground loop. Additionally, it is important to ensure that the generator is properly grounded to the earth. This can be achieved by connecting a grounding electrode, such as a ground rod, to the generator frame. The grounding electrode provides a low impedance path for fault current to flow back to the source, which helps to protect people from electrical shock. In summary, understanding the differences between 3-prong and 4-prong receptacles, proper neutral bonding, and ground loop prevention are essential for safely connecting a generator to a home's electrical system. Always consult with a qualified electrician for any electrical work to ensure that the installation meets all applicable codes and standards. Here are some additional points to consider regarding generator connections and safety. Portable generators should be used in well-ventilated areas to prevent carbon monoxide poisoning. Carbon monoxide is a colorless, odorless gas that can be deadly. Never operate a generator indoors or in enclosed spaces. Install carbon monoxide detectors in the home to alert occupants of the presence of carbon monoxide. Before starting a generator, make sure that all appliances and lights are turned off. This will prevent overloading the generator. Do not overload the generator. Overloading the generator can damage it and create a fire hazard. Use heavy-duty extension cords that are rated for the generator's output. Do not use damaged or frayed extension cords. Keep the generator dry. Do not operate the generator in wet conditions. Store gasoline in approved containers and away from heat sources. Turn off the generator and let it cool down before refueling. Never refuel the generator while it is running. Inspect the generator regularly for any signs of damage. Have the generator serviced by a qualified technician if needed. Follow the manufacturer's instructions for operating and maintaining the generator. Be aware of local electrical codes and regulations regarding generator installations. Obtain any necessary permits before installing a generator. Educate all household members on the safe operation of the generator. By following these safety guidelines, you can minimize the risk of accidents and ensure the safe and reliable operation of the generator. Remember that electrical work can be dangerous, so always consult with a qualified electrician if one is not comfortable performing the work. The information provided is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician for any electrical work to ensure that the installation meets all applicable codes and standards. Proper grounding and bonding, neutral switching, and adherence to safety precautions are essential for protecting people and property from electrical hazards. Generators provide a valuable source of backup power during emergencies, but it is crucial to use them safely and responsibly. With proper planning and execution, a generator can provide peace of mind and ensure that the home remains powered during a power outage.